Good day, ma'am. We are here again to present to you virtually our final presentation in our subject, Highway and Railroad Engineering. By the way, my name is Jeorlly Ancheta, and today we will be talking about the pavement design together with its three important subtopics, which are the following. First, the specifications and tests on pavement materials. Second, the pavement design factors. And lastly, the design of rigid and flexible pavements as per Indian Road Congress or IRC, in which it will going to be discussed by the other member of the group later on. So when we say pavement design, it talks not only about the visual reference or the aesthetics of the pavement, but it talks more on its core. Fundamentally, a paved surface performs two basic functions. First, it helps guide our drivers by giving them a visual perspective of the horizontal and the vertical alignment of the traveled path, thus giving drivers information relating to the driving task and the steering control of the vehicle. It means na yung ating pavement, siya yung nagga-guide sa ating mga drivers and yung ating pavement din yung nagsiset ng limitations kung hanggang saan lamang pwedeng mag-drive yung ating mga motoring public. Second, it supports vehicle loads. Yung load induced by the moving vehicles ay natratransfer doon sa ating pavement, and then mula naman doon sa ating pavement natratransfer papunta doon sa ating subgrade at a level that is acceptable and bearable depending upon the engineering property of our subgrade. As with any structure, the underlying soil must ultimately carry the load that is placed on it. A pavement's function is to distribute the traffic load stresses to the soil at a magnitude that will not shear or distort the soil. Typical soil-bearing capacities can be less than 50 pounds per square inches and in some cases as low as 2 to 3 pounds per square inches. When soil is saturated with water, the bearing capacity can be very low. And in these cases, it is very important for the pavement to distribute the loads to the soil in such a way as to prevent failure of the pavement's structure. Next, pavements are among the costliest items associated with highway construction and maintenance, and are largely responsible for making the U.S. highway system the most expensive public works project undertaken by any society. Because the pavement and associated shoulder structures are the most expensive items to construct and maintain, it is important for the highway engineers to have a basic understanding of the pavement design principles. So it says here that pavement are among the costliest. Bakit? Kasi a huge portion of the budget allotted for the highway construction ay napupunta doon sa pavement pa lamang mismo. And as we can notice, unlike doon sa ibang projects na makikita lamang natin sa iisang lugar, ang ating highway system ay tuloy-tuloy at makikita natin ito sa buong mundo. For example na lamang dito sa Pilipinas, we have 33,018.25 kilometers of roads as of October 15, 2019, according doon sa road data provided by the government. And 97.18% nito ay already paved na. It's either concrete or asphalt. At yung natitirang 2.82% nito ay still unpaved. So it's either gravel or earth road pa lamang siya. So imagine kung gaano kalaking halaga yung inilalaan para sa highway construction. And now, let us proceed to the specifications and tests on the pavement materials. First, we have the soil. Soils are used as subgrade embankment and shoulders. Stabilized soils are often used in sub-base or base courses. In soil, we have two evaluations or tests of properties. Una dito yung ating index properties. We have the grain size analysis and consistency limits and indices. For grain size analysis, we have two methods na ginagamit. Una, yung safe grain size analysis wherein it is capable in determining the particle size ranging from 0.075 millimeters to 100 millimeters. And we use hydrometer grain size analysis naman for the particles that is less than 0.075 millimeters in size. Whereas particles na mas malalaki sa 100 millimeters can be categorized visually. While soil consistency is the strength with which soil materials are held together or the resistance of the soil to deformations or rupture. Second was for the strength of soil. We conduct shear test, which is either a laboratory or field test to measure the shear strength properties of the soil or rock material or of discontinuities in soil or rock masses. And we conduct bearing tests to determine the ultimate bearing capacity of the soil. And lastly, we conduct penetration tests. And we have here next the list of the important quality control tests on soil. So you can just read it here because I'll be no longer explain this. Moving on, let us proceed to the aggregates. A major component in road construction, mainly used in granular bases and sub-bases, bituminous courses, and cement concrete pavements. Kapag dito naman sa ating aggregates, we have two types of aggregates. We have the natural aggregates and the artificial aggregates. Natural aggregates, these are obtained from rocks, and artificial aggregates can be obtained from broken brick, ballast, and slag. Tapos, meron tayo dito yung sources ng ating natural aggregates. Una, from igneous rocks. Forms from the cooling of molten material which are very good for bituminous courses and cement concrete pavements. Pangalawa, yung sedimentary rocks, deposition of granular materials that is good for sub-base and base courses. Pangatlo, yung metamorphic rocks, transformation due to heat and pressure which are good for base courses, bituminous courses, and cement concrete pavements. Tapos meron tayo ditong evaluations or test of properties sa ating aggregate. Una dito yung para sa strength. Nagkakandak tayo ng crushing strength test. Crushing value test of aggregates provides the resistance of an aggregate sample to crushing under gradually applied comprehensive load. Pangalawa naman para sa hardness. To determine the hardness of an aggregates, we conduct different kind of hardness tests such as Los Angeles abrasion test, Devial abrasion test, and polish stone test. Pangatlo, para sa toughness. For toughness, we conduct impact test. The safe aggregates should be dried in an oven and then filled in a cylindrical steel cup and tamped with 25 strokes by tamping rod. Pang-apat, para sa durability, we conduct soundness test. Soundness test determines an aggregate's resistance to disintegration by weathering and, in particular, freeze-thaw cycles. Panglima, para sa ating shape test as flackiness index, elongation index, and angularity number. And panghuli, para sa ating adhesion with bitumen, we conduct stripping test. The stripping value of the aggregates is determined as the ratio of the uncovered area of the aggregate, expressed as percentage. Bitumen and tar adhere well to all normal types of aggregates provided they are dry and not exceptionally dusty. And for the continuation of the pavement materials, let us hear from Kenneth Kim, Agapito. And Kenneth, take it away.
Hi ma'am, I'm Kenneth Kim Agapito and I will be reporting pavement material binders. Types of binders. Number 1, natural, rock, or like asphalt. Naturally occurring bituminous binder. This type of binders is also used for coatings, roofs, floor tilings, soundproofing, waterproofing, and other building construction parts. Number 2. Bitumen. Conventional bitumen are paving grade bitumen and industrial grade bitumen, cutback, bitumen emulsion, modified bitumen, and modified bitumen emulsions. Makikita natin itong bitumen sa mga highway. Bitumen is a last residue obtained from fractional distillation of crude oil. It is in black or dark brown color. Also, it is a viscoelastic material which does not have distinct melting point. It gradually softens when heated and more solid at low temperature, and more liquid at high temperatures. Bitumen also has adhesive and waterproofing properties and forms a good bond with a variety of aggregates. Evaluation or test of properties. Number 1. Penetration test. It is arbitrary empirical number. Next, depth of penetration of standard size needle under standard test conditions. Next, very easy to perform at field level. Helps in classification and traceability. This type of test is to determine the hardness or softness of bitumen by measuring the depth of millimeter to which a standard loaded needle will penetrate vertical in 5 seconds. Softening point test. It is arbitrary test to indicate the temperature at which bitumen is more of a liquid and less of a solid. Next, higher softening points indicate higher resistance to melting on road. Higher resistance to melting indicates higher rotting resistance. This type of test is to determine the consistency of bitumen or kung gaano siya katibay pag namabasa. Number 3. Ductility test. It is arbitrary empirical test to measure the cohesive strength. Next, cohesive strength is loosely related to the fatigue strength. Next, testing temperatures may vary from country to country and from grade to grade also. Itong nakikita nating sample is to measure the distance in centimeter to which it widened before breaking. Number 4. Frost breaking point. It tests low temperature properties. This mode of failure likely to place only when temperature are less than 0 degrees Celsius. It is also used for determining the breaking point of solid and semi-solid asphalt. Number 5. Viscosity test. Viscosity at 135 Celsius is a fair indicator of the coating ability of bitumen. Viscosity at 65 degrees is a replacement of for softening test, and it is an indicator of the ability of bitumen to resist rotting. This test is to measure the degree of fluidity of bitumen sample. It ensures the quality of the bitumen used as a binder by giving a measure of a fluidity at a particular temperature. Next is thin film oven test. This test stimulates the process of aging bitumen during mixing and laying. Sample is kept in an oven at 163 Celsius for 5 hours. TFOT aged bitumen can be tested for penetration, softening point, ductility, viscosity, and etc. This test is most commonly used to stimulate the STA of binders. This test is used to measure the combined effect of heat and air on a thin film of bitumen or bituminous binder in permanent renewal. Other tests. Penetration ratio or penetration index. It indicates temperature susceptibility of bitumen. Typically, Pi values are ranging from around -3 to around +7 for highly blown, low temperature susceptible bitumen. Next, wax content. It may give negative effects in bitumen like increased sensitivity to cracking or plastic deformation in asphalt concrete pavements, but in other cases, wax may even show positive effects on bitumen, such as increased stiffness at higher temperatures, leading to improved resistance to rotting. Number 3, specific gravity. It is used for pavement construction and it can also help in identifying the source of the bitumen binder. Number 4, water content. It is used to know the amount of water to prevent foaming when bitumen is heated to a temperature above its boiling point. Number 5, matter soluble in organic solvents. It determines the degree of solubility in trichloroethylene of asphalt material with little to no mineral matter, resulting with soluble portions. They represent the active cement constituents. And the last is flash points. It is used to distinguish between flammable fuels such as petrol, also known as gasoline, and combustible fuels such as diesel. It is also used to characterize the fire hazards of fuel. So, this is my report in pavement material binders. Thank you.
Good day everyone, my name is Jearlyn Gumarag. So our topic for today is pavement design factor.
Under pavement design factor, we have 3 factors to consider. First is the traffic loads, next is soil support capability, and last is environmental factor. First is the traffic loads.
Because the primary function of a pavement is to transmit and distribute wheel loads of vehicle to the supporting subgrade information about the traffic strip is required. Pavement must be designed to serve traffic needs over a period of years. Therefore, the volume of traffic and the various type of vehicle using the facility must be estimated for the pavement's anticipated life. So, traffic loads. One of the primary function of a pavement is load distribution. Therefore, in order to adequate design a pavement, representative loading characteristic must be presumed about the expected traffic it will encounter. Loads the vehicle forces exerted on the pavement, like trucks, heavy machinery, airplanes, can be characterized by the following parameters. First is individual tire loads, axle and tire configurations, typical axle loads limit, repetition of axle loads, traffic distribution by direction and lane, and traffic projection, current, volume, and growth rate. So traffic loads along with environment damage pavement over time. The simplest pavement structural model assert that each individual load inflicts a certain amount of unrecoverable damage. This damage is cumulative over the traffic of the pavement, and when it reaches some maximum value, the pavement is considered to have reached and its useful service life. Next is a traffic assignment is made based on historic record of traffic volumes on comparable types of highways and the anticipated function of the highway under consideration. So, the design year traffic volumes are estimated at 25,000 and 20,000 vehicles per day, respectively. On the major and minor roads, the posted speed limit are 45 miles to 72 kilometers per hour on the major road and 35 miles 56 kilometers per hour on the minor. There are sidewalk facilities along all approaches, and the intersections serve as daily volume of 2,400 non-motorized road users. Next is the percentage of trucks. The traffic analysis procedure determines the repetition of an equivalent single axle load, or what we call ESAL, This parameter is defined as the equivalent number of application of an 18,000 pound single axle load during the pavement design life. So equivalent single axle load or ESAL based on AASHO road test results. The most common approach is to convert axle configuration and axle loads of various magnitudes and repetitions, or what we call mixed traffic, to an equivalent number of standard or equivalent loads. The most commonly used equivalent load is in the US is 18,000 1B. Equivalent single axle loads normally designated ESAL. This is the loading format used in FPS 21. Next is the effect of truck traffic on a pavement can be dramatic. Tests have shown that a single unit fully loaded 80,000 pound truck can cause pavement damage equivalent to that caused by 6,000 automobiles. This illustrates why carefully made estimates or expected traffic are critical to proper pavement design. Last is traffic is separated into classes. Each class is defined by an average daily traffic range, the average number of heavy trucks expected on the pavement during the design period, and the appropriate type of street or highway. First class is very light, less than 50 autos per day, less than 7,000 heavy trucks expected during design period. Like parking lots, driveways, light traffic farm roads, school areas and playgrounds, sidewalks and bicycle paths, golf cart paths and tennis court. Second class is light, up to 200 autos per day, 7,000 to 15,000 trucks expected during the design period. Residential streets, rural farm roads, parking lots of less than 500 stalls, airports, 7,500 pounds maximum gross weight. Third class is medium, up to 700 autos per day, 70,000 to 150,000 trucks expected during design period. Urban minor collector streets, rural minor collector street, parking lots more than 500 stalls, airports, 15,000 pound maximum gross weight. Class 4 is medium, up to 4,500 autos per day, 700,000 to 1,500,000 trucks expected during design period. Urban minor arterial and light industrial streets, rural major collector and minor arterial highways, industrial lots, truck stalls, bus driveways and loading zones, airports, 30,000 pounds maximum gross weight. Class 5 is heavy, up to 9,500 autos per day, 2 million to 5 million trucks expected during design period. Urban freeways, expressways, and other principal arterial highways. Local industrial street, major service drive or entrances, airports, 60,000 pounds maximum gross weight. Class 6 is very heavy. Unlimited autos. 7 million to 15 million trucks are expected during design period. Urban interstate highway, some industrial roads, airports over 60,000 pounds maximum gross weight. So that's all pavement design factors about traffic loads. Thank you.
A pleasant day po, ma'am. I, Domingo Rodito, will be reporting all about soil support capability and environmental factor. So first, it says here in soil support capability, is the ability of the subgrade to support loads transmitted from the pavement is one of the most important factors in determining pavement thickness. So subgrade is a native material that are found underneath a constructed road or a pavement, no? And the subgrade must serve as a working platform to support construction equipment and as a foundation for the pavement structure that support and distribute traffic loads. So before the construction of a pavement, we all know that there are some preparations that must needed to be done. For example, is we see a heavy equipment flattening the soil surface using the motor grade and compacting the soil using roller machine, and Thus, it is essential also not to evaluate the strength of the subgrade before beginning the structural design of the pavement. Next, we have here the figure shows that spread of wheel load through the pavement structure and onto the subgrade. Here in figure, it shows the subgrade is at the bottom, and on top of it, we have the pavement structure and the load. Next is, if sufficient pavement thickness is not provided, the applied loads could cause greater stresses on the subgrade that it can resist. So we have a minimum and an average thickness of a pavement, and the minimum is 288 or 11.8 inches. If this thickness has not been followed, this may result in deflection of the pavement and ultimately in its failure. So commonly nakakakita tayo ng mga deflection and failure sa mga pavement. And in street and highway construction, the subgrade provides the foundation for the pavement. So subgrade is very important, no, in street and highway, because this is serving as their foundation. So different types of soils have different abilities to provide support. So not all soils have the ability not to support different types of loadings. Next is, we have soil is classified for road and street construction in order to predict subgrade performance, and on the basis of a few sample tests. The American Association of State and Highway Transportation Officials, the AASHTO classification system for soil, is commonly used as a test for subgrade support value. So next we have here, and according to the AASHTO system, soils that have approximately the same general load carrying capabilities are grouped in classifications of A1 through A7. So the AASHTO systems made a classification not to know how strength or capable the subgrade to withstand the support loads, and through this they classified as A1 through A7, and in general the best highway subgrade soils are A1 and the worst are A7. So the classifications here is using the sheave analysis, plasticity index, and liquid limit of the soil being tested. Next, here we have the environmental factor. Temperature is the most important environmental factor to be considered in design of pavement. So in the case of asphalt roads, temperature affects the resilient modulus of the surface course. In very hot conditions, asphalt layers lose their stiffness. At low temperatures, asphalt layers become brittle and cracks are formed. So kapag napapansin natin, kapag dumadaan tayo sa Kalamagi papuntang ISU Ilagan, the road there is asphalt and there are failures and deflections there, no, due to temperature. And consider also the reason why does this happen is sa mga heavy trucks, and yung mga commonly na nakikita nating cracking here is block cracking, edge cracking, alligator cracking, and reflection cracking. So in case of rigid pavement, temperature stresses are developed also. Curling of concrete is also possible due to variations of temperature in the top and bottom layers of pavement. And lastly, moisture variations or precipitation from rain affects the depth of the groundwater table. Good drainage facilities should be provided for good strength and support. The groundwater table should be at least below 1 meter from the pavement surface. Kapag napapansin natin yung drainage system natin dito is umaapaw, yung end is parang napupudpod, and yung mga gates niya dito is na natutuklap, and then yun nagkakaroon rin siya ng failure. So that's all. Thank you.
Good day everyone, I am Sheenah Telan and I will now discuss to you the measurement of pavement quality and performance. So the design procedure for pavements originally focused on the Pavement Serviceability Index or PSI as a measure of pavement quality. However, the Pavement Serviceability Index is based on the opinions of panel of experts, which can introduce some variability into their determination. Since there are different experts, opinions will also be different, kaya magkakaroon ng variation. As a result, efforts have been undertaken to develop quantitative measures for us to acquire quantitative basis. Quantitative measures of pavement condition that provide additional insights into pavement quality and performance and that correlate with the traditional Pavement Serviceability Index.
So, some factors that are regularly measured by highway pavement agencies now include the International Roughness Index or IRI, friction measurements, and rut depth. So, these are the products of the efforts in developing quantitative measures of pavement conditions. So, first is the International Roughness Index or IRI, determined by measuring vertical movements in a standardized vehicle suspension per unit length of roadway. So units of IRI are reported in inches per mile. The higher the value of the IRI, the rougher the road is. Friction measurements. To estimate friction, a standardized test is conducted under wet conditions, using either a threaded or smooth tire. Although other speeds are sometimes used, the standard test is generally conducted at 40 mph using a friction testing trailer in which the wheel is locked on the wetted road surface and the torque developed from this wheel locking is used to measure a friction number. Next is the rut depth. A measure of pavement surface deformation in the wheel paths can affect roadway safety because the ruts accumulate water and increase the possibility of vehicle hydroplaning. So this is a picture of rutting. As you can see, it is the path of the wheel. This deformation may accumulate water, greatly reducing braking and steering effectiveness. Next is cracking. So for flexible pavements, there are 4 types of cracking. First is the longitudinal fatigue cracking. This is parallel to the road length, a surface down cracking that occurs due to material fatigue in the wheel path. This can accelerate over time and it requires significant repairs to protect against water penetration into flexible pavement structure. Next is transverse cracking. It is perpendicular to the road length. It is the result of low temperature that causes fractures across the traffic lanes, resulting in increase in pavement's roughness. So, connected siya sa IRI kasi kapag maraming transverse crack, mas magiging rough yung ating road surface. So, next is alligator cracking, a consequence of material fatigue in the wheel path, generally starting from the bottom of the asphalt layer. Such material fatigue creates a path of connected cracks that resembles the skin of an alligator, thus called alligator cracking. Lastly is the reflection cracking, which is wala siyang picture pero it happens when an existing road with cracks at nalagyan lang ng overlay. So yung cracks na mayroon sa dating pavement surface, magre-reflect ngayon sa ating overlay. Next is faulting. So for traditional JPCP or joint plane concrete pavements, rigid pavements, joint faulting characterized by different slab elevations is a critical measure of pavement distress. Faulting is an indicator of erosion or fatigue of the layers beneath the slab and reflects a failure of the load transferability of the pavement between adjacent slabs. Faulting is associated with increased roughness and will be reflected in IRI measurements. So there's a failure in the load transferability, thus nagkakaroon ng elevation. As you can see in the picture, kapag mayroong ganitong ating road surface, tataas din ang IRI. So, punch out. For continuously reinforced concrete pavements or rigid pavements, those built without expansion or contraction joints, fatigue damage at the top of the slab is often measured by punch outs, which occur when the close spacing of transverse cracks cause in high tensile stresses that result in portions of the slab being broken into pieces. Punch-outs are associated with increased roughness and are reflected in the IRI measurements. So next is the design of flexible and rigid pavements. So first is flexible pavement. A flexible pavement is constructed with asphaltic cement and aggregates and usually consists of several layers. This figure is a representation of a section of a flexible pavement. We have here 4 layers. The bottommost layer is the subgrade or the soil itself. Yun yung mismong soil kung saan natin ipapatong yung ating pavement. It is upper 6 to 8 inches and is usually scarified and blended para magkaroon tayo ng uniform material bago siya i-compact. So, ang subgrade ay kinokompact for it to develop a better engineering property. Field density test is the test in which we are able to know kung gaano nakadense ang ating subgrade bago siya latagan ng subbase. And next is our subbase, which is 4 to 10 inches, usually consists of crushed aggregates. Next is the base, which is also 4 to 10 inches. It is often made of crushed aggregates which are either unstabilized or stabilized with a cementing material. And the topmost layer is the asphaltic concrete layer, which is a mixture of asphalt, cement, and aggregates. It is usually 2 to 4 inches. So this is a picture of a flexible pavement that is very familiar because there are a lot of flexible pavement in our highway system today. So pavement system design, principles for flexible pavements. The primary function of the pavement structure is to reduce and distribute the surface stresses on an acceptable level at the subgrade. A flexible pavement reduces the stress by distributing the traffic wheel loads over greater and greater areas through the individual layers until the stress of the subgrade is an acceptably low level. So, as we can see sa ating figure, yung distribution ng load sa bawat layer ay in a shape of a cone. Meaning, palaki ng palaki yung area na naa-applyan ng load hanggang ma-reach niya ang ating subgrade. Pagdating sa subgrade, mas malaki na yung area na sinasakop ng load. Therefore, reducing the stress. Kasi 'di ba, stress is force over area. Paglaki ng area ay ang pagliit ng stress. Next is the rigid pavement. A rigid pavement is constructed with Portland cement concrete or PCC and aggregates. As shown in the figure is a representation of the section of a rigid pavement. We have here 3 layers. The bottommost layer is still the subgrade or the soil, which usually scarified and blended before it is compacted. Next is the base course, which is 4 to 8 inches but is optional depending on the engineering property of the subgrade. So kung magandang engineering property ng subgrade, maaaring hindi na maglagay ng base course. And the topmost layer is the Portland cement concrete slab. As you can see here, we have a load transfer device called dowels. Dowel bars are short steel bars that provides a mechanical connection between slabs without restricting horizontal joint movement. And we have a construction joint, a sewed form or tooled groove in a concrete slab that creates a weakened vertical plane. It regulates the location of the cracking caused by dimensional changes in the slab.
So this is a picture of a rigid pavement, which is also familiar because we have a lot of rigid pavement in our highway system.
So pavement system design principles for rigid pavements. So rigid pavements distribute wheel loads by the beam action of the Portland cement concrete slab, which is made of material that has a high modulus of elasticity on the order of 4 to 5 million psi. This beam action, illustrated in the figure, distributes the wheel loads over a large area of the pavement, thus reducing the high stresses experienced at the surface of the pavement to a level that is acceptable to the subgrade soil. The purpose of the pavement is to transmit the loads to our subgrade at a larger area, therefore smaller amount of stress. So the essential difference between flexible and rigid pavement is the manner in which they distribute the load over the subgrade. For rigid pavement, because of concrete's rigidity and stiffness, it tends to distribute the load over a relatively wide area of subgrade. The concrete slab itself supplies a major portion of a rigid pavement's structural capacity, while flexible pavement, inherently built with weaker and less stiff material, does not spread loads as well as concrete. So therefore, flexible pavements usually require more layers and greater thickness for optimally transmitting load to the subgrade. So that is all about our report. I am Sheenah Telan again, and thank you.